is an energy. It's not increasing the kinetic energy, so the temperature doesn't go up. And so we have another latent heat. We'll call this one a latent heat of fusion, evaporation. Vaporization is probably the best word. So let me say that again. It's the latent heat of vaporization. We are turning it into individual pieces. And on this graph, it would look like this. And so what I'm trying to add to our discussion is when you go to calculate energies, it's not just change in temperature, but it's also change in phase. Change of state. And so let's refer to this energy as the latent heat. And again, we call it a latent heat. That's Latin for hidden, because the early scientists knew they were adding energy. And that's what I'm doing right now. If I put a thermometer in here, this thermometer would say 100 degrees Celsius. And I've been adding energy. And as I keep adding energy to it, it still says 100 degrees. The temperature doesn't go up. That's why probably when you were younger and you were learning to, boil food or, I don't know what you boil. Maybe you boil your tomatoes or your veggies. And you put a pot of boiling water on there, you turn up the flame really high at first till you get it boiling. But once it's boiling, it's not going to get any hotter. You leave the flame on high, all you do is boil it away faster. And so that's why I'm sure your mom or dad instructed you, well, now turn down the fire. Once you've got your noodles in there and it's boiling, turn it down. It's not going to get any warmer. You're just wasting money and gas as we heat it. You're just boiling away the water quickly. And that's what we're seeing right now. We finally caught up to our experiment here. We have gotten to this point. We're somewhere about maybe here on the chart. We have boiled away, if I can kind of look at it, some of the water. We were roughly at about 400 milliliters. Looks like now we're maybe at about 325. And so maybe we've boiled away 75 or 70, 60 milliliters of water. And so we're right here on our graph where we have already hit 100 degrees. We've added some energy, but it's going to take a lot of energy to get all of it. And so that's why we call it the latent heat of vaporization. And so again, I just want to emphasize that in addition to worrying about the energy to change its temperature, we also have to consider the energy to change its state, the breaking of the bonds. Because remember, the liquid, from the solid to the liquid, we semi-broke the bonds. Now we're going to break the rest of them. And for water, this number is about 540 calories per gram. And note that this number is quite a bit bigger than this number. So it takes a lot more energy to turn it from the liquid into the gas. This evaporational state is really, really a lot of energy. And I'll say more about that in just a second here, but that's why I was able to catch up with my experiment. I knew that my experiment here would take a long time to boil this all away. This is a huge amount of energy. And that's what I want to calculate here for you. So now that we have got it to a boil, let's ask the question, how much energy then is it going to take to completely boil away all that water? And so let me put a Q again. And let me kind of do the same thing that I did here for the change from a solid to a liquid. I have then the idea of this latent heat. And the latent heat is really telling me how much energy per gram. So I need to multiply it by how many grams do I have in order to figure out how much energy has to go into that, in this case, the beaker of water. So let's use the symbol L, and this time we'll put a V for the latent heat of vaporization. By the way, the other direction would be going from the vapor into the liquid. And so it would be a condensation. And so this is the latent heat of condensation also. But we like to use the word vaporization, and so we put a V. Just like back here, this is the latent heat of melting or fusion, but we like to call it the fusion part of it. Probably because when we deal with water, we start with the liquid and we have to do something to vaporize it, or we have to do something to fuse it together. But I want to emphasize, because you need to understand this as you do the homework and on the test, that if it goes the other direction, the energy has to be released. Here, I have to give it energy to boil away. But when it condenses, it would give that back off. Now, today's weather has been really warm, and lately it's been warm. In fact, we even smashed a record yesterday. I don't know if you know. I mean, actually, I was getting excited. We smashed a record. We hit 98, which is incredibly high. I think the past record was like 91, and it was back in the 18-somethings. It was incredible. But I thought maybe we'd hit 100, and that's just, wow, incredibly rare. I wanted to take some time. I didn't. I was wondering if, Santa Barbara ever hit 100? And I don't know if it has. Ron's shaking his head. He thinks it has hit 100, but very, very, very rare. I mean, the 90s are very rare. So we've had warm days, but the reason I'm saying that is if you could imagine back on a cool day, and particularly a cool morning, maybe way back in January or February when we were still coming to school, and you got up and it was cold. If you went in to take a shower, a lot of times you'll turn on the hot water, and by the time you're done with the shower, you will notice that there is all this moisture on the mirror, on the windows. And if you took a long shower, maybe there's even moisture on the walls. But it's also warm and cozy in the bathroom after that. Why? Well, when that water condenses, as it's floating around the room, and it condenses on the mirror, it releases that energy. It's the reverse of what I'm doing right now. What I'm doing is I'm putting energy into it, and this vapor is going around the room. But when it hits something and condenses, or even if they hit each other and make rain, it has to release that energy. And so in my bathroom, it gets nice and warm and cozy in there because it's released all of that. And the walls get warm and then warm the air. And so it's nice and warm by the time I get out of the shower. Because I know when I was getting up and I got into the shower, it was cold. It was cold in the house. It was cold in the bathroom. That's why I turned on this hot water. That's why I stayed in there for way too long. And then it's nice and warm and cozy in there. And if this is a storm, and for us, a storm coming out of the Gulf of Alaska, what ends up happening is it comes out of the Gulf of Alaska and it condenses. We call that rain. But what I want to emphasize is when it does rain, that condensation is a release of energy. And so when you say a storm has energy, where did it get it? Remember the conservation of energy? Where did it come from? And that's where it comes from. It comes from the condensation. And so as it condenses, it releases that energy. Maybe it shows up as wind. And so this wind blows really, really hard. And that's where its energy is. Now, of course, I guess ultimately you would say, well, the condensation came from the molecules hooking together. Where did it get that energy? Well, it came from evaporating off the ocean, which came from the sunlight. So what I'm kind of doing now is evaporating it, and as it goes throughout the room, it's going to condense and release that energy back into the room. And so that's kind of what a storm is. And that's why, again, in Santa Barbara, we get these big storms, and we go, oh yeah, big storms, and we get a little mudslide. I mean, that's probably our biggest problem is they block the road, and, mud flows down our steep hills. And, of course, wasn't that long ago before the Montecito mudslides. And, they were devastating. They were devastating because the energy came from the mud flow. But they weren't devastating because the energy came from the condensation of the water. We just don't have that much condensation because we don't have that much moisture. We don't live in a high humidity area. So where are your storms going to be really powerful? Yeah, it has to be where there's a lot of moisture in the air. It's why we don't get hurricanes. But hurricanes, if you look at them, they always start in the tropics and the subtropics, because that's the place where it gets the most sunlight, which evaporates it, and that is the energy source for the storm. And so that's what I'm trying to say here. There's both a forward and a back to this. Well, before I talk too much, I better jump back over here and say, okay, let's calculate this finally. Okay, so if I come over here, I can put in my 400 grams. I can then put in this latent heat of fusion, and that's 540 calories per gram. What does this come out to be? 54 times 4, 16, 21. And so that is a 216 and 3 zeros. So 216,000 calories then is the amount of energy required to break all of the bonds and boil away this 400 grams of water, which, as I said, this is why I knew we would catch up to it. It's still boiling over here. I can look at this thing and go, well, we still got 225 grams more to boil away. We haven't even boiled away half of it yet. It's going to take a lot of energy. It's going to take a long time for all of this to boil away. Now, I should add to this, although I can't do it, if I had a giant container that were catching all this vapor, once it all boiled away, it would now all be in the gas state. And so now it would be back to looking like this, and bouncing around. And if I continue to add energy to it, so that's why if I captured it and continued to put the flame under it, now its temperature would go up. And so its graph would look like this. And then to calculate how much energy that would be, I would go back to the MC delta T. And of course, this would be the H2O in the gas state. And let me emphasize again, as I said earlier, don't assume that the specific heat in the gas state is the same as the specific heat as in the liquid state. It is not. And so in our case, we need to look up the specific heat of the gas. And the gas is about 1/2 calorie. It's coincidentally just about the same value as when it's in the solid state. And that's just coincidental. That's not normally the case for our materials. And then we can warm it up some temperature, and I can't really catch it or warm it up. So I won't put a number there, but this would be then the additional energy as we warm up the gas. And so if we went from, say, 100 degrees Celsius to 200 degrees Celsius, I would have to put 100 in here. And then multiply all this out and then figure out how much would it take to warm this up. And then if I added them all together, I eventually would have the answer to how much total energy does it take to go from the solid state of an ice at negative 20 degrees to, and then if I go all the way up to the vapor state, I would have to add them all together. And that's what I really want to emphasize. So as I started this lecture saying, look, this will give us a chance here today to look at the numbers. Let me emphasize, you get the numbers two different ways. When they're within a state, it's changing temperatures. And when it changes state, there's a latent heat. And you got to account for each of those. Okay. Let me turn on the projector again, because I spent this whole time talking and calculating water. But just like there would be a specific heat for each material, there is also a latent heat for each material. And this is it. And so I was working with water, And so if I come over here and say, okay, here's the water, it tells me how much energy it is in calories per gram. There's the 80. There's the latent heat of melting. Here it is in some other units. I won't worry about those units. And then here's the temperature. And so if I'm doing a problem, I have to know if I started below 0 degrees and I go above 0 degrees, besides figuring out the energy based on the change in temperature, I got to figure out the energy because it's going to change its state. See, and then here's the water, and here's the 100 degrees, the boiling point, and then here's that 540, they have 39, they have it a little more accurate. And so here's the latent heat of vaporization. So again, if I'm doing a problem, I need to know what the boiling point is of my material, in this case water, so that if I go above 100 degrees, I know that I have to include the energy of the latent heat of vaporization to calculate the energy. And so your author has given you 5 different materials, and so I'm sure as you do problems, they'll involve aluminum and gold and water and oxygen and nitrogen, and so how much energy does it take to change the phase? And so again, I think the word latent heat gives it away. It's a common mistake when students go, how much energy did it take to go from ice to water? They just calculate the temperature change. They don't include the latent heat. Really dangerous because you're missing a biggest part of the energy. And maybe dangerous is too strong, but it's just wrong. There's energy to break the bonds. I guess the dangerous part comes in there if you don't realize it. This is why, on the good side, if you're out on a hot day like today, and you decide to go down, and our beaches are kind of opening up again. I don't know if we're allowed to play volleyball yet, but if you get out on the beach and go to East Beach here and play some volleyball, you can get really, really hot. And the way to cool down your body temperature is take something cold. Now, if you just do cold water, then all you're doing is putting cold water inside of you, and then the water warms up to your body temperature. And so it warms up from 0 degrees to a body temperature of about 37. Okay? But if you were to chew on ice, or I think better still, a snow cone. Because if you take a snow cone, the snow cone is really chunks of ice. And it's got a little flavoring. Or maybe even better still, ice cream. Ice cream tastes really good, and it's got chunks of ice in it. But that's the key. The chunks of ice, when you put those in your body, the energy they absorb is not just warming up, but it's also breaking the bonds. And so you will cool down much, much quicker and much, much easier with the chunks of ice. And so that snow cone, or just the ice in a glass, or the ice cream, than you will with that cold drink, even if it's just water. Of course, you're evaporating. And so let me add back to that. Do you remember the last chapter we said, how do humans cool themselves? And we said they evaporate. And we talked about dogs. And remember I said that it's harder then to evaporate when you're in a moist environment. So like it feels hotter in Florida than it does in, say, Las Vegas. Now you can see some numbers here. And if you look at these numbers, if I come back over here, this is really why. Oh, where'd that number go? Oh, here it is. Oh, I don't know if you're going to be able to see it. but this number here, this 216,000, this is the energy that would leave my body if I were to evaporate 400 grams of water. Now remember, 400 grams of water was not much. I'll come back over to here because my experiment is still going. And I wanted it to still go. And I've gone way over time, so I'll have to take our 20-minute break here, and there's still more to talk about in this chapter. But I just wanted you to see, amazingly to me, how long this has been going on, and I still have about 150 grams of water left in it. And I'll just turn it off since I'm about to end this lecture, and then I'll have to swap out the material, and I don't want it to be too hot. But I do want to emphasize now instead of just talking about the concept that our body cools itself, I know that if I drank a glass of water, this much water, it's not even really that much, just 400 grams, which is, 0.4 of a liter, and my body evaporated it, my body, the evaporation alone would be this much energy. Now I say alone because my body's temperature is 37. And if I drank the water, let's say it was cold ice water, it would then be starting at 0 degrees. So as I drank the ice water, so no pieces of ice, just the ice water, my body would first warm it up to 37. Then as it evaporated, it would be going from, or equivalently of going from 37 to 100. So this would take the 32,000. Sorry, that's melting it. This is the one I want. Okay, so if I just drank the water, this 40,000 would be needed to warm up the water to begin to evaporate. And then this is the main key. This is the actual evaporation, way more than this. And so this is important, true, but it's not nearly as important as this. And so that's why I was saying your body is an excellent cooling mechanism by evaporation. And if you end up in a moist environment like Florida, which gets in the way of this, you can get incredibly hot, not because so much the temperature outside is really hot, but you just can't cool yourself. You're limiting this. This is not happening at a fast rate anymore. And so as you warm it up, you still have this, but you don't have this. Of course, like I said, it would be better if I had ingested this as ice, because then I would have to have this much energy to break the ice apart. And if it was cold ice, then it would even be this much, which this is kind of minor, so this is small. But just ingesting that ice, I got to break the bonds of the ice to make the liquid. Then it's got to turn into to the vapor state, so equivalent to get up to 100 degrees. Then it's got to actually evaporate off my skin, and that's a lot of energy. And that's why I want to show you one last thing here. Your author does a really good job at then showing you that if you were in a different environment, somewhere that is not Santa Barbara, you might come across what we call a heat index. Because as you look across this graph that says the relative humidity and the air temperature, let me just pick on 85 degrees. Because today in Santa Barbara, we will probably be at a high of about 85, but our humidity is going to be really low. And so we're going to be around 10%, maybe 15%. If the sea breeze picks up, depending on what direction, we might get to 20 or 25%. But even if we get as high as 35%, you see, this is what our bodies are used to. And so at 85 but low humidity, our body is evaporating so easy that we like to say it feels cooler than 85. The real temperature is 85, but it's so dry out there, and so this would be like Las Vegas, that it feels cooler. Of course, this time in Las Vegas, it's probably closer to 100 degrees, but low humidity, so it only feels like 90 degrees, because your body is just having this incredible ability to evaporate. But Florida, Miami at 85 degrees might be something like 90% humidity. And that would be feeling to your body like 102 degrees. And your body's just having a hard time cooling itself. That's why I said in the other lecture, it's surprisingly to think, oh, the temperature is only 85 in Florida, and people are dying. They're overheating. Mm-hmm. This is why. Because their bodies can't cool themselves, evaporate. And so that's what the heat index is for. It's actually not really a temperature. It's not really a science thing. It's an added biology thing. How does your body feel if you can't cool itself? So all these things can feel really, really warm. I mean, look at this. I mean, you end up in the tropics, and it may only be 85 degrees, but it's nearly 100% humidity. And so I know when I like to go to Cozumel. It's usually about 85. But it's also like 100% humidity, and it just feels like 108. And so it's just really, really hot. And it's sticky hot, and so much that as I sweat, it doesn't even evaporate. It just runs down. And so I like to be in the desert when at least, okay, if I'm sweating and it evaporates away, I don't on. And so I just make sure I keep drinking water. But I end up in the tropics, and oh my goodness, it just keeps running down, and then my shirt is, my shorts are soaked. Well, like I said, I'm way over time here, so let me say the end of this. Let's take our 20-minute break. I'll swap out a little bit of the equipment, and we still need to talk about a few more things at the end of this chapter, and that will be the end of the chapter, and then also where the test will go to. All right, see you in 20.